You're probably thinking, blah, 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 get to the numbers, get to the example. Let's see how these things get used. It's one thing to talk about these equations of theoretically, but I need to see numbers plugged into those things so I can actually see how they work. So let's do that. Let's actually look at, so let's go back to our example and think about how we do hypothesis testing. For the one-way repeated measures, the approach is the same. Where our null is going to be, I think all the means are equal, pre equals post equals follow-up. The alternative is, well, not all of them are equal, right? There's at least a difference there that's significant. 3, we're still going to assume alpha is 0.05, and because it's a topic we're talking about, if you see that there's people that are repeatedly measured like this, you're likely doing repeated measures of ANOVA. If there's only 2 levels, could be dependent samples t-test, but once you get to 3 or more repeated measures, repeated levels, it's a repeated measures ANOVA, not a dependent samples t-test. So one thing I do note here is that pay attention to the description in a word problem or something, because the way this is set up, you have the subjects here and stuff, but this could be a one-way between groups. It could be a one-way repeated measures, depending on how it looks like. If you see that they've provided you with subject means, right? So you're doing a problem on a test or on a practice problem, and you can't tell, is this a repeated measures, is this between groups? If all of a sudden there are subject means provided to you, it's a good chance, like 99.99% accuracy here, that it's a repeated measures ANOVA, not a between groups. Because if it was between groups, there'd be no reason, because these are going to be 3 different people. Why would I average them to get us an average over there? So that's a good sign that it's repeated measures. So step 5, we need to talk about degrees of freedom. We need to find an F critical value so that we can actually make our decision rule. Okay, so between groups is the same as it was before. And again, I'm using G here, but we don't have to. It's the same as it was before. When we did a one-way between groups, it was K, right? So G minus 1, same thing as K minus 1, whatever it is. We have 3 of them. Minus 1 means I have 2 degrees of freedom between groups. Great. Easy enough. We talked about within groups before, that was a total number of subjects, and we lose 1 degree of freedom, 1 for each of the 3 groups. So here I'm saying it's N minus G. It's the same thing, N minus K. Okay. It's actually good to not get so tied up in the specific letters of things, because as you go from class to class, or from different textbooks, different instruction, they can use different letters to mean different things, and you got to be able to adapt to that. So here I'm calling the number of groups G, and in the past I called it K. Doesn't matter, they're the same thing. I'm defining for you that G is the number of groups before I define K as the number of groups. So it's a different definition, or a different letter, but the same definition. You got to learn to sort of roll with it, because you're not going to see consistency across classes. I mention this because this was a huge thing for me, going from this class, 320, to the next one that I took in stats, which was at that time called Psy320. It's now called Psy385, 45 US. The instructors used different notation for equations, and I was so hung up. I had memorized all the equations in 320, and I was stuck with those notations, those letters, those things, and it became actually a hindrance. It made it much harder to learn the new material in the next class. I had to sort of let go of all that and learn to sort of be a little bit more flexible with it. So it's good to start doing now, be able to understand that letters can mean different things, and just figure out what the letters mean in the context of the problem, and then sort of roll with it. So N minus K, N minus G, same thing. I have 30 subjects, so 30 scores. I really only have 10 participants, right? But I have 30 scores, and that's what N represents here, the capital N. I have 3 groups, so 30 minus 3 is 27. Now for subjects, it's little n minus 1. Well, little n is, well, I have 10 participants in each group. So 10, little n is 10 minus 1 equals 9. And then because, like I said, that the error term here is an interaction between subjects and groups or time, it really is an interaction. Like we're going to multiply n minus 1 times g minus 1. So we're now talking about 10 minus 1 times 3 minus 1 equals 9 times 2 is 18. Like I said, these two are subcomponents of this one, the degrees of freedom within groups. They should add up. 18 plus 9 does equal 27, so that works out. So I've taken my 27 degrees of freedom and broken them up into 9 and 18 degrees of freedom, so that works. And they should all add up to the total, which is still the capital N, big N, minus 1, which is 30 minus 1 equals 29. So I either have 2 plus 27 is 29, or I have 2 plus 9 plus 18 equals 29. Either way you want to look at it. You don't add these up twice. Don't add 27 and 9 and 18, because this 9 and 18 are part of the 27. Okay, so that they all add up. So my F critical, I'm going to use the degrees of freedom between groups. But instead of using between the degrees of freedom within groups, since the within groups is not what I'm going to use as my denominator when I get to my F, I'm going to use error instead, this one here. So the 2 degrees of freedom I need now are between groups and error. So it's now 2 and 18. So my F crit with 2 and 18 degrees of freedom is what? Well, I don't know. I got to look it up. Let's look up on a table and see what it says. So here's my F table. It's a little bit goofy because there's writing still in there, but I think you can see it. So I need 2 and 18. So let me see if I can find a place where I can put it where it's not 2. So here's 2 degrees of freedom. When you go down to 18 degrees of freedom, just here. So we can make that a little bigger. So you can see it. So there, look, there's 2 degrees of freedom up here. There's a second column. If I go down to 18 degrees of freedom, it is, so 18 is here. 3.555 is my critical value. 3.555. So F critical, 2 and 18 is 3.555. So my decision rule is going to be if F observed is larger than that number, 3.555, I'm going to reject the null hypothesis. Okay, so we've taken our one-way between groups, and our degrees of freedom are a little bit more complicated because, again, we're taking everything about within groups and splitting it into subjects and error, which means splitting up the sum of squares and splitting up the degrees of freedom. Okay, so we split that up. So there's more degrees of freedom defined. So it's now, instead of being 2 and 27, like it would be if it was a one-way between groups, it's now 2 and 18 because we're doing a one-way repeated measures. All right, we're using the degrees of freedom that corresponds to the random error we're going to use in the F in just a second. So 2 and 18, that's our critical value. So on to step 6, which of course is where, you know, the meat of the analysis is, because that's where we're going to find our F observed in order to compare it to our F critical. So step 6, calculating F observed. To do this, we're going to calculate the sum of squares. I know this looks like sum of squares S, but sum of squares. Use the sum of squares to calculate the mean squares, and then use all that to calculate the F observed. Okay? Sum squares, we use those with degrees of freedom to get the mean squares, and then mean squares to get F. All right, so let's do that. So first, let's walk through again how to do the sum of squares for total. Now I actually have the answer here. So my squares total is this number, just as a safety net. Sort of like when you watch a baking show and they already have one sort of already made. That's the number we're shooting for. So again, this equation is each individual score in each group minus the grand mean. So there's going to be 30 of those. All right, the grand mean is 15.767. All right, so let's do that. Let's try to figure out if we can make this work. So let's do 30 of these things. So before I go over, sum of squares total equals. So my first score is 15. 15 minus 15.767. I'm going to square that. And keep going. Plus 20 minus 15.767 squared plus 14 minus 15.767 squared plus 19 minus 14.767 squared plus 25 minus 15.767 squared plus 23 minus 15.767 squared plus 19 again. 19 minus 15.767 squared plus, I'll keep going down here, plus, can't even see that, plus, that was 19 again, so 8 minus 15.767 plus 9 minus 15.767 squared plus, so let's see if I can just go through and we do this so it lines up. So 9, so they got 23. That ends the first, all the pre's, right, up to this point. 15.767 represents all the pre's. I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is the first 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So now I need to go to the next, to the pre. I'm sorry, of the post. So now, see if I can just do this a little bit differently. So 13, 14, 8, 18, 14, 23, 17, 14, 7, 11. All right, so that should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Going to take me all the way through post. So I'm going to keep going to follow up. 16, 18, 12, 22, 17, 25, 25, 16, 12, 7, 14. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's everybody. So now I need to subtract out the Grammy. All right, I think they're all squared, subtracted. So really, if you're doing this, you go through and just start working these out and keeping track of them as you go, because it's really hard to do this all in one go. You can do it, but one little mistake and you've screwed the whole thing. So like 15 minus 15.767 squared is 248. What? 15 minus 15.767. 15 minus 0.767 equals, oh, that was a weird number. If I square it, it's 0.588. So now anytime there's a 15 somewhere, is there any other 15s? Doesn't look like it. I see the 15 there. Nope, only 15. Okay, well, you can find then 20 minus 15.767 equals 4.233 squared. 17.918. Let's make sure I did that right. 20 minus 0.767 equals, yep, squared, yep. 14 minus 15.767. 15 equals squared 3.122. 122, yeah. And you would keep going. I'm not going to spend more time doing it. You keep going, keep doing that for all of them. Add them all up. And when you add them up, if you carry everything to 3 decimals, you should get 813.367 as your answer. Okay, that should be your sum of squares for total. Alright, so let's move on to sum of squares between groups. This is the same as was before, but let's go through it and make sure we're all on the same page. This one's a lot easier because we're dealing with just the means of each group and not every individual subject. So we only have 3 means, which means we need to do this 3 times. That's a lot easier than doing it for every single subject over and over again. Alright, so let's do this. Right here. So sum of squares between groups equals, I need to take my first mean, which is 17.5. Subtract from the grand mean. I'm going to square it. And it says multiply by n. Well, how many people did it take to get to 17.5? So there's 10. So 10 times that is going to be for my first group. Okay. I'm going to add to that. The next one is 13.9 minus 15.767 squared times 10. The last one is 15.9 minus 15.767 squared times 10. Alright, so this one we can figure out. 17.5 minus 15.767 equals 1.733. Need to square that. It's 3.003 and then times 10, which is 30.033. So this is 30.033. 13.9 minus 15.767 equals negative 1.867 squared is 3.486 times 10 is 34.857. Okay, something doesn't seem right. 13.9 minus 15.767 equals that squared that times 10 equals that. Oh, so this one's really small. Okay. So we got 15.9 minus 15.767 equals 0.133 squared is 0.018 times 10 equals 0.177. Yeah, so this is 0.177. If I add those up, 30.033 plus 34.857 plus 0.177 equals 65.067. All right, so that's good. 65.067. All right, easy enough. The between groups is like my favorite. It's easy. One per group. It's not really complicated. You're going to keep track of a lot of stuff. All right, let's figure out the sum of squares for subject. So this one's sort of in between. It's not as easy as the between groups, but it's not as bad as the within groups or total either, because we have to do one per subject. So instead of doing it 30 times, we're going to do it 10 times. All right, so I need a mean for each subject minus the grand mean squared times the number of groups. All right, so this time you notice that the G is outside of the parentheses, outside of the sum, I mean. So we can just do this one time, which is nice. Sum of squares for subject. All right, so SS for subject equals, so I know I have 3 groups, so it's going to be 3 times whatever happens right inside the bracket here going forward. So the first person has a mean of 14.667 minus 15.767 squared. Plus, next person is 17.33 minus 15.767 squared plus. Next person's 11.333 minus 15.767 plus, square there. The next person is 19.667 minus 15.767 squared. And the last one for this row anyway is 18.667 minus 15.767 squared. Keep going. So I just did subject 1, 2, 3, 4, 5. So now you keep going. 23.667 minus 15.767 squared plus 17.333 minus 15.767 squared equals 11.333 minus 15.767 squared plus 7.667 minus 15.767 plus 16 minus 15.767 squared equals, so right down here, sum of squares S equals 3 times, and let's just work these out. $14.667 minus 15.760, 14.667, 14.667 minus 15.767 equals negative 1.1 squared is 1.21. So we get a 1.21 plus, is there any other 14.667s? Nope. So 17.333 minus 15.767 equals 1.566 squared is 2.452 plus 11.333 minus 15. Crap. So one thing, my brain was doing two things at once. So I noticed this is here, so is this. So there's another 2.452 there. Okay. So 11.333 minus 15.733 minus 15.767 equals negative, is that right? 11.333 minus 15.767 equals, yes, negative 4.434 squared. So I'm getting a 19.660. Which means down here I also have a 19.660 because they're the same. Okay. And so 19.667 minus 15.767 equals 3.9 squared 15.21, and then 18.667 minus 15.767 equals 2.9 squared equals 8.41. Okay. And then down here, 23.667 minus 15.767 equals 7.9 squared is 62.41. And then this one, 7.667 minus 15.767 equals negative 8.1 squared is this one, 65.61 plus the last one here is 16.667 minus 15.767 equals 0.16 minus 15.767 equals 0.16 minus 15.767 equals, 0.233 squared is 0.054. So let's add all that up. There's that. So 1.21 plus 2.452 plus 19.660 plus 15.21 plus 8.41 plus 62.41 plus 2.452 plus 19.660 plus 65.61 plus 0.054 equals 1. So okay, this part inside the brackets equals, so we need 3 times 197.128 times 3 equals, so I get a slightly different number, so 591.384 instead of 367, but really close. Again, slightly rounding. Okay. So this 3 again is for groups, adding them all up, and I'm, it's likely, if I here somewhere, but if you are going through this and you see if there's an error someplace in here, what the error is, leave a comment in the space below and let me know, and I can sort of figure it out. But it's likely just rounding. 3.367384. That's fairly close. Yeah, that's it. That's the sum of squares for subjects. All right, to get error, we're going to take the sum of squares for subject that we just found, and we're going to subtract it from the sum of squares within groups, which is what it was before in the one-way between groups ANOVA. So it's actually one of the more tedious ones, but it's the same as it was before. It's actually straightforward, just kind of a pain in the butt. So it's the sum of squares within groups is each individual score minus the group means, which means, again, we're doing this 30 times. All right. So let's lay that out. Sum of squares within groups equals be each individual score, 15 all the way through there. All right, so I'll do this in groups of 5. So 15, 20, 14, 19, 15, 20, 14, 19, 18, 25. And then starting here, 23, 19, 19, 19, 8, 9, 23. Okay, so that's the first group, so it's all minus 17.5 squared plus this minus 17.5 squared plus this minus 0.5 squared plus this 17.5 squared plus this 17.5 squared. Same group, so same mean, 17.5 squared plus 17.5 squared. Of course, I keep going. Then you go to the next group. 13, 14, 8, 18. 13, 14, 8, 18, 14. And then 23, 17, 17, 14, 7, 11. So here I'm subtracting out 13.9. All right, that's the second group all the way through. Third group, 16, 18, 12, 22, 16, 18, 12, 22, 22, 17, 25, 16, 12, 7, 14. Let's try to get the last means of 15.9. Okay, there's all of those, all 30 scores minus their own group means. All right, I realize this 23 looks pretty awful, but All right, 23. So there's 30 different scores. These are all the scores in the first group minus their group mean. These are all the scores in the second group minus their group mean. And then all the scores in the last group minus their group mean. You're going to subtract, square, and do all that stuff. And if you do all that, what you're going to get is this 748.3 number, or something really close to it. So in order to get the sum of squares for error, right, so now we're down to here again, sum of squares for error, you're going to take the 748.3 and subtract out the sum of squares for subject we found on the previous thing. If you use the other 17.38, whatever it is, it's fine. But I'm just use what I have written down here. So 591.367 equals. So subtract those two. $748.3 minus 591.367 equals 156.933. And this is our sum of squares for error. Okay? 156.933. That's the number that we're looking for our random error term that we're going to turn into a mean square and use in our f when we go to calculate it. All right, so that's the sum of squares for error, which requires finding the sum of squares within groups, subtracting the sum of squares for subject that we just found in order to get the error sort of isolated alone. So whichever way you find the sum of squares, once you get to this point, you can then create an ANOVA summary table. So you found your sum of squares, we know our degrees of freedom, we can start plugging them in. Now this looks a little different than our one way between groups ANOVA summary table, because there's some things more things to keep track of. So notice the things in bold, those are things that are important, they're going to be using for our purposes. So we found the sum of squares for between groups, and that's the same. We found the sum of squares within groups, and that's also the same as it is for one way between groups ANOVA. But we took that and broke it up into those, the subject effects and the error effects that both are part of within groups. We also broke down the degrees of freedom, 27 broken down into 9 for subject and 18 for error. And then we also have total. So the mean squares that we care about, the ones that we're going to be using, are the ones that are in bold. The other ones really were just a means to an end. We found that within groups and subjects so that we can subtract them and get error. So we don't really need a mean square for total, because we're not really using it for anything, nor do we need a mean square for subject or within groups. You can put them, if you divide and put them there, it's fine, but you don't really need them. All right, so let's go through and at least these out. So remember to get mean squares, all right, I'm going to be dividing this way, those two, divide those two this way. So 65.067 divided by 2. 65.067 divided by 2 equals 32.534. All right, so 32.534 is my mean square there. The only other one I need to do is the one for error. All right, so that's 156.933 divided by 18 equals 8.719. So this is 8.719. So to get my f, I'm just going to divide those two. 32.534 divided by 8.719 equals 3.731. Okay, 3.731. Let me do that again just to make sure. 32.534 divided by 8.719 equals 3.71731. Yeah, okay. So we had found our critical value earlier in step 5, right? So I'm just bringing it over here. It's from the F table. So we're going to make our decision. Since 3.731 is larger than 3.555, right? Just barely, but it still is. We're going to reject the null. So again, remember, what was the null? The null was that pre, post, follow-up, all their means were equal. That was our null hypothesis. Our alternative was that, that they're not all equal. So by rejecting the null, we are making a conclusion that there is some evidence that that THC does have an effect on memory. Now we already knew that from our dependent samples t-test from before, but we now are stating it with this follow-up in there, and we can actually look at those differences a little bit more and figure out if there is a rebound effect after THC sort of leaves your system. Repeated measures ANOVA assumptions. And we talked about the assumptions around the t-test, around the between groups ANOVAs, and for the most part, 2 of the 3 assumptions are the same. So what are the assumptions? We assumed homogeneity of variance. Right, we're assuming the variances of the different levels are roughly equal. We assumed that we had enough people, or that the population was normally distributed, so we can actually assume a normal distribution of the sample means and stuff. That's based on the central limit theorem. So that still applies whether it's an independent samples t-test, dependent, between groups ANOVA, within groups ANOVA, or repeated measures ANOVA. What does differ is that in a between groups, we assume that the participants are independent. So we know that by having repeated measures, we don't have independent samples. So we don't assume independent samples anymore. So that goes out the window because we know they're not independent. But we do assume something instead. We assume that the correlations, I know we haven't talked about correlations yet, that's actually in the very next topic, but let's say that the rank ordering between participants stays roughly the same, so the correlations should stay roughly consistent. So the correlations between trials are approximately equal. So what we want to see is here's the correlation between pre and post. It's 0.508. Here's the correlation between pre and follow-up. It's 0.694. Okay. So those are different, but they're not too far apart. But here's the correlation between post and follow-up. It's 0.903. It's much larger than it is these other two. So is this a problem? So we're assuming that the correlations between times should be roughly equal. And one thing you should notice about correlation matrices is that the values up on top here just repeat at the bottom, because the correlation between pre and post right here is the same thing between post and pre, which is why these two numbers, this number and this number, are the same number. It doesn't matter which direction that it's in. So another way of saying this, and this is actually more than really necessary. The actual assumption is a little bit more complicated than this, but this is a sort of simplified. What we want to see is that the relationships, the way that people move across time, should stay consistent, which is the whole point of us trying to identify the sum of squares per subject, to identify the consistent subject variance. For us to take that out, we have to assume that they're being fairly consistent. There is some consistent responding of participants. So this is really just another way of saying that when subjects go from time 1 to time 2 and then time 2 to time 3, that there really should be some consistency across those. If you think about my hand here, those that are at the top as you move across time should stay close to the top. Those at the bottom should stay close to the bottom as they move, to stay relatively consistent. That's what this is saying, that we're assuming that the consistency sort of continues across all the groups, so that the correlation should be roughly the same. Now the reason for this, at least one way of thinking about this, is if we want to look at how the means change across time, well, nothing else should really be changing. The variances should stay consistent, and the degree of relationships between the time points should stay consistent, or else if everything is changing, comparing the means to one another becomes sort of less interesting. Not less interesting, but less conclusive, because the means are changing, but so are the variances, and so are the correlations, and so like everything is changing. So there's really more going on than just a change in level of memory. Lots of other things are happening. So we want the variances around, like in our example, around recall to stay consistent, and we want the correlations between time points to stay consistent, so that when we look at mean differences, we can say that there is a mean difference that explains what's happening, because everything else is sort of staying consistent. All right. So we want the correlations between time points to stay consistent. It looks like here, like maybe not. Maybe we're having an issue, because this, remember the highest correlation, maybe not remember, but we're going to talk about it next. The highest correlation you can have is a 1. 1 is the highest. Well, with post and follow, we're getting closer to that. We're getting 0.9. But between pre and post and pre and follow-up, you know, they're at 0.51, 0.69. They're not quite as strong. This is a much stronger correlation. So does that represent a problem? Well, remember, we only have 10 participants. So the previous matrix might look like we violated assumptions. There's only 10 subjects. So it's likely that difference between the 0.9, the 0.6, or the 0.9, the 0.5, they're probably not that big a deal. But there are places like in SPSS where those kinds, the kind of test I'm talking about actually gets tested. If you do repeated measures of ANOVA, you're going to get a test, something called sphericity, which is what this test is sort of looking for, is the consistency across responding across time points. And if that's violated, which it often is, which is the problem with repeated measures, then you have to figure out some way to deal with it. There's things like the greenhouse geyser adjustment. There's the wind felt adjustment. There's lower bound estimates. There's all kinds of things you can do to try to fix this, to try to figure it out. And what it does is they adjust the degrees of freedom to sort of, I don't know, to basically increase the F critical, so that even though you're violating this equality of correlations across time, if you still found a significant effect, then you can trust it. So these corrections that you'll see, because in SPSS, when you run this for a lab, you're going to get the test for sphericity. If it's significant, that's a problem. And then it's going to provide you with a table, whether you ask for it or not. You actually don't ask for it, it just gives it to you. It's going to give you a table of a bunch of corrections. And you're going to see things like greenhouse geyser and wind felt. Wind is like H-U-Y-N-H, that kind of wind felt. And I think lower bound, maybe some others, as corrections of this, because it is a typical problem. So, you know, this having correlations stay consistent is an issue that oftentimes pops up in these repeated measures of ANOVA that makes it difficult to interpret. So then you got to do these corrections to make it more meaningful. All right. So what about? All right, so we talked about the assumptions, which 2 of them are the same. There's this sort of new one, this consistency of correlations across time. All right, great. What about, you know, we already did a dependent samples t-test and saw that pre and post were significantly different. So now we have 3 levels. We've now just said the same thing. Well, all right, there's a significant difference between groups, but it doesn't tell us where. So we're back to this idea of multiple comparisons. I tested all 3 groups. It told me there was a significant difference someplace, so that not all means were equal. So we need to go through and do follow-ups. Now, the thing about multiple comparisons or follow-up t-tests or follow-up tests after repeated measures of ANOVA is that there are no just post hoc adjusted tests, like the Tukey test, Fisher's, all these other ones, Dunnett's, Fay, all these other types of tests don't exist for repeated measures for reasons that I'm not going to go into right now, but the testing differences between repeated measures is a little more complicated when it comes to these sort of post hoc adjusted things. So what do? Well, just figure out dependent samples t-test, compare pre to post, pre to follow-up, post to follow-up. Do those tests, do maybe with a Bonferroni correction or something like that, so that you are keeping the family-wise error rate in check. And maybe don't do all comparisons. Maybe you don't care about doing everything. Maybe I just want to do pre to post and then compare post to follow-up. I don't need to do pre to follow-up, right? I can just do those two, and if they're both significant, then awesome. It means that we have a significant decrease in recall and then a significant increase in recall, and we can be done, right? That's great. And maybe do, again, a bond floating correction or something like that to make sure you're not overinflating alpha. When you have more means, let's say you have something like I had mentioned, like math ability across grades. So you have like 9th, 10th, 11th, 12th, maybe even go back farther, 6th, 7th, 8th, 9th, 10th, 11th, 12th. So you have 7 years of data when you want to look at sort of people's change in math ability across time. Well, doing these sort of individual difference things are going to be problematic. You're going to lose the overall picture. A lot of times you see math ability is a trend, right? So if I'm looking at just 2 years at a time or doing these little comparisons, you're going to lose the bigger picture. So there are these things called trend analysis that you can do. Again, this is beyond the course, but just sort of planting the seed in your brain that in a class like 485, we'll start talking more about. We can actually test for different types of trend. Like what kind of trend might I be talking about? It's very simple things. Like if I'm looking at math ability, maybe I'm looking at linear trend. Does the trend across the years, 6, 7, 8, 9, 10, whatever, do they follow a line? Is there a linear trend? Maybe it's a curvilinear trend. Maybe there's some quadratic trend in there where they're actually, faster at first, or slow at first and they speed up, or they're really fast at first and slow down when it comes to learning. Those types of trends you can actually test to see do the means actually fit a trend. That's something you can do when you have a lot of different means and you're trying to look for some kind of patterns across them and using all the groups at one time as opposed to just looking at 2 groups, 2 individual groups at a time, which loses the sort of bigger picture. So this is sort of keeping the bigger picture in mind and focusing on the bigger patterns across the means. So what are some advantages of repeated measures? I mentioned some of these along the way, but let's repeat them again here just for completeness. So it does eliminate subject differences from error term, or at least the consistent subject differences, right? So it identifies the sum of squares for subject, which are the consistent differences between people, and it removes it. It takes it out of the sum of squares within groups. So we have a smaller error term, which means greater power. And we can get greater power with fewer subjects. Right? So if this were an independent samples or between groups ANOVA, I would need like 30 different subjects to be randomly assigned to different conditions to compare them. Well, with this, I just need 10. I have 10 people. They come back for follow-up. They come back for post. They come back for follow-up. So it's a lot fewer subjects. Now that might seem like weird. Why do we care about that? Well, lots of times in research, subjects have to be paid, right? You have to find them. There's a lot of effort to go and try to recruit subjects to get them to come into your lab or come into your space, come into wherever it is you're doing your research. So getting the subjects, recruiting them, paying them, all that stuff is actually time consuming and cost money. So if you can actually get more out of the subject, meaning, use them in a repeated measure sense, get more information out of the same subject while you have them, that can actually be a lot more efficient sort of use of the subject's time and your time and money and everything else. So we can get by on fewer subjects, which is good. And sometimes it's the only way to address the problem. If I want to look at how THC affects recall, and I want to see if recall, if looking at the recall, before and after ingesting THC, and then after sort of THC exits the person's system, it's sort of difficult to do that as a between groups, study. I mean, you can have one sample that eats regular Rice Krispies, another one sample that eats the Rice Krispies with THC in it, and you see there's a difference and stuff. There's some ethics issues there because you're basically not telling them that they're getting THC or something. But again, to be able to compare the same people to see how much they recover afterwards is not something you can easily do as between groups. Right. So this example illustrates that case. Maybe not perfectly, but it does give you some illustration of that. And like certain things you just can't. Like if you want to look at You know, again, if you want to look at people's trajectory and their math ability over time, you need to look at the same person over time. You need to look at to be able to track them and do a repeated measures design. So there's certain things that just make more sense to address using this kind of analysis. Okay. What are some disadvantages? Well, just like with any repeated measures, carryover effects are an issue. Carryover effects meaning that anytime you do something to somebody, it's likely the very next time they show up to do it again, they could be affected. And so counterbalancing and changing the order of things for different subjects actually would be better if possible. Now, it's not possible to counterbalance the order of like no THC, THC, and then THC wears off. But in this case, what we could do, because what could happen in our example with carryover effects? All right, subjects are exposed to list 1, the first list they get. And then when they come to list 2, it's possible to get some interference or carryover from list 1. If they're remembering words from list 1, it's making them sort of lose points or whatever because they're not writing down words from list 2. And then when you get to list 3, you got list 1 and 2 both that are interfering. So one way to counterbalance this effect would be to make sure that there aren't certain words in list 1 that affect list 2 and so forth, is that every subject, you have 3 lists. Every subject gets a different list as list 1, a different list as list 2, and a different list as list 3. So you're not getting the same carryover, the same effect of words carried over for each subject. So if I have list 1, 2, and 3, subject 1 comes in, they get list 2 first, list 3 second, list 1 third, in terms of the 3 different time points. And subject 2 gets list 3 first, list 1 second, list 2 third. Makes sense? So it's a way of counterbalancing that regardless of what condition they're in, the words from the previous study may impact their ability to recall, but at least everyone's being impacted differently. So if you're getting a similar trend for recall and that kind of stuff, it's not because of the words, because everyone got a different set of words in different orders. That's a way of sort of counterbalancing the effects so that you're not getting the same carryover for everyone, which could actually then impact your study and be explaining a better explanation for your study than the actual intervention. Right? So we want to use counterbalancing to avoid. You can't avoid carryover, but you can make sure that the carryover sort of is randomly distributed and is different for different people so that you can sort of eliminate it as an explanatory variable in your study. Repeated measure designs may tip off the subjects to what you're trying to test. And as soon as if they have an idea what they think you're trying to test, they may respond and act differently. And that can be problematic. You may get these sort of subject characteristics or response characteristics where they're being reactive to you or something, or trying to do something, to give you what you want. And if they get it wrong, it could totally screw up their responses and things. So that can be problematic too. And just like, there are certain studies that only make sense as repeated measures. There are some that don't, or that don't work very well as repeated measures. If you need to trick participants, like surprise them or scare them or pull one over on them sort of repeatedly, it's going to get old. Anything that requires tricking a participant would likely work once, but not going to work over and over again. So those kind of things don't really work well for repeated measures. And things where repeated measures don't make sense. If I want to compare males to females or men to women or something like that in a study, I can't do that as a repeated measures design. I can't say, okay, today you're male, come back tomorrow and be female, right? There's certain things that just don't work as repeated measures if you want to do a comparison like that. And the last part is, again, about effect size. So this is really a simple extension of what we did for t-test for related samples. You could do things again like the dependent samples version of a Cohen's d. You could apply that here. Use the largest differences between the probably like pre to post, and the 2 largest means. If you use the pre-test standard deviation and create a Cohen's d, you could. And but more likely, more realistically, you're going to calculate something like an eta squared. You can be used for repeated measures data as well, especially since the between and total are unchanged between a repeated measures and a between groups ANOVA. You can use the eta squares or the omega squares. Those things will still work. You're going to get essentially the same results because the between and total haven't changed. Now, in the omega squared, it gets a little bit weird because are you using the mean square within groups or the mean square for error to sort of do the adjustment, which is why I don't really have omega squared listed here in repeated measures. And let's just stick to, for repeated measures, we'll just stick to eta squared. So if you're doing a repeated measures ANOVA and you're asked to do effect size, just stick to eta squared, between over total. It's simple. You don't have to try to figure out what error goes where and what. There are some adjustments that can be made to eta squared that if you continue in stats, you'll learn more about. These things called like partial eta squareds as opposed to regular eta squareds that can give you some more meaningful information about the effect size for data. But just for the sake of time and ease and maybe a bit of sanity on all of our parts, let's just stick to regular eta squared as our effect size measure for ANOVA, for repeated measures ANOVA. So if you're asked to do a between groups, like a one-way between groups, a one-way factorial, you may be asked to do eta squared or omega squared. But for repeated measures, we're going to stick just to eta squared, keep it simple. Okay. So for our example, we could take the sum of squares for time, the between groups sum of squares, which is this 65.067 divided by our total, and we get that, 0.07999. We get roughly 8% of the total variability can be explained by change over time. So when looking at all the variability, the differences between subjects' responses when it comes to recall of these words, the change over time accounts for just 8% of it. That's because there's a lot of variability between the subjects at each time point. Lots of variability going on. People just remember more or less words, have better or worse recall. Yes, the THC does seem to shift them down and then up, but that really only explains a very small proportion of the overall total variance. Even though this seems small in terms of psychological experiments and things, 8% is not necessarily a bad number. Somewhere around 10% is probably commonly seen as a strong effect for a lot of psychological stuff. That's because just humans are complicated, a lot of things going on. So if we're looking at psychological phenomenon, it's really hard to explain a huge proportion of it with a simple effect, with one effect like time like this. So this 8% may seem small, but likely is not necessarily that small. And that's it for repeated measures ANOVA. All right, so we talked about between groups one way, we talked about a factorial between groups, and now we've done this sort of repeated measures one way. I do want to point out, I had mentioned earlier, you can continue going this. You can do a factorial repeated measures. It's possible, can. Sometimes it's a little hard to think of what that means, but factorial repeated measures is possible. It's something like, again, think about our study. We have pre, post, follow-up, and maybe this is with, so maybe we do this with like placebo, and then this whole thing gets repeated again with the same people. Pre, post, follow-up with a sort of active THC. Like here, they're just being told they're eating THC, but they weren't, and here they're actually getting THC. This is where sort of counterbalancing might become important too for different people. But again, this is the same people, subject sort of 1 through subject 10, right? Going through the whole thing. You can do this as a factorial repeated measures. You have both placebo and active, pre-post follow-up. You can get the interaction between them. So there is something, factorial repeated measures, that we're not going to cover. It's not in the course, but it is something that exists out there, and you could learn more about it. Again, 485, Psy320 US covers topics more like factorial repeated measures and something like a mixed ANOVA, which there are different versions of the idea of mixed ANOVA, but I'm thinking about a mixed between repeated. So go back to our example again. So let's say I'm still doing THC, but I have pre, post, follow-up, and maybe I bring in 2 different groups where I have non-users, so people who don't regularly use THC, which is a group that we started with in our example, but then maybe we have some regular users come in. All right, so people who have done who regularly sort of ingest THC, whether smoked or eaten or whatever, and maybe they're not as impacted by the presence of THC in their system. So we can actually, this part ends up being between groups, and this part's repeated measures. So we can look at, is the difference in change from pre-post to follow-up dependent on whether someone's typically non-user of THC or a user of THC, and we can actually look at interactions and things where we have some between groups components and some repeated measures. So this is a mixed ANOVA, which is also possible combining both between and repeated measure stuff together. All right, so I just wanted to leave it this. This is where we're going to leave ANOVA, but we haven't covered like everything. Actually, there's still even more than this if you really get into it. But the 2 bigger things we're not covering, we're not talking about, is factorial repeated measures and mixed ANOVAs that you can learn more about if you take a class like Psych 485 US, which is offered every fall, I believe. We offer Psych 485 US every fall semester. That's it.